All right, we're ready to go now. If I can get the slideshow to set up, which doesn't seem to want to do. It will open. Here we go. Now, before we get started on that, let me make this last announcement. It's about my office hours. If you haven't figured it out yet or haven't realized it, we are now in the second mini-term. We just finished half of the term as of last Thursday. Okay, Friday was the beginning of the second half of the term. Now, what that means for me is I pick up the second mini-term physical science class Tuesday, Thursday afternoon, 3:15 to 5:45, followed by a lab 5:45 to 7:45, every Tuesday, every Thursday. Okay, so there goes a huge chunk of my office hours. So right now my office hours on Tuesday, Thursday will be 12:15 to 3:15. Done. That's it. That's all I got on Tuesday, Thursday. Now, technically, it also changes my Monday, Wednesday office hours because I was staying till 4:45 every day. Actually, most days 5:15. But now with staying till 8 o'clock on Tuesday, Thursday, technically I'm leaving earlier on Monday, Wednesday. So Monday, Wednesday had been 2 to 4:45. Now, technically, it's 2. No, I have no office hours on Wednesday. That's right. I'm supposed to leave right at 2 o'clock. I won't be leaving at 2 o'clock. I will be here probably till at least 4:45 every day, but I have to put it on the board because we only are supposed to be working 40 hours a week, so I have to put it on that I leave it at 2 o'clock. But in reality, most days, except for rare exceptions, I'll be here until probably at least 4:45, more likely 5:15. So that's on Monday, Wednesday. But technically now all my office hours on Monday, Wednesday are 11:15 to 12:15, which is my lunch hour. But I'm in the office then. I eat my lunch in my office, so come see me if you need to see me there. Or after 2 o'clock, you'll still find me here most days. Okay? So, any questions before we get going on Chapter 2? Now, a few people haven't started the test, and I think just about everybody hasn't finished the test. Okay? So, let me know when during my office hours, which just got much shorter, you want to do that. Now, if you want to do it right after class, I've got a class in here, but I believe the room next door was open, wasn't it? Yeah. So, unless they added a second mini-term class there. So, you can work on it right after class if you want to, or during the office hours I just talked about. So, if you can catch me before any of my classes, I'll find the room for you to work on while I'm teaching. Okay, but because my office hours just got shorter, it makes it a little tougher on you, I realize. 12:15 will be fine. Wait, okay. Yeah, 12:15 today is fine. Now, I'll be in this room at 12:15.
Well, I'll leave that class at 12:15.
Okay. Okay, so if you don't catch me here in my office, now a student came by yesterday and wants to meet with me about his student degree plan. So I'll be meeting with him, but I can give you a test. We'll find a room and put you in. Okay. So, any questions? All right, Chapter 2 continues a lot of what we were doing in Chapter 1. It's talking about special kinds of functions. Chapter 1 was just the algebra of functions, basically. Okay, we talked about what you do with functions. Most of our examples were polynomial functions. A few of them were actually rational functions. Now, I tried to introduce those to you when we had them. In 2.1, we're focusing just on quadratic functions and their models, not polynomials in general, but quadratic. What do we mean by quadratic? Maximum exponent of 2. That's correct. No fractional exponent. Okay, let's go back to this. What do we mean by polynomial functions? What's a polynomial? An expression whose only exponents are whole numbers, positive or zero whole numbers. No negatives, no decimals, no fractions as exponents. Coefficients, yeah, no problem. So those are polynomial functions, okay? So a quadratic function is one where, again, it's a polynomial function, but the maximum exponent is 2. So it basically only has exponents of 0, which is no variable at all, just a constant, 1 linear, and 2 quadratic. Okay? And we'll do a little bit about the modeling. Okay, never mind. Okay. All right. One of the things our objectives will be analyze the graphs of quadratic functions. You already know about these. You've already told me about them. We'll write quadratic functions in standard form. Now, this is something a little interesting here. Of course, all of it's interesting. I heard someone say, quite loudly, Diamond is here, right? Okay. A quadratic equation has a standard form we're used to. Ax squared plus bx plus c equals 0. That's the standard form for a quadratic equation. However, we're going to define quadratic functions to have a slightly different standard form. We'll talk about that when we get to it. We'll use those results to sketch graphs of functions. They're really into graphs of functions, right? Find the minimum and maximum values of quadratic functions in some real-life applications. And these are places that we're pretty interested in most of the time in real life. So let's first start with the graph of a quadratic function. Okay? This section, you'll study graphs of polynomial functions, all types of polynomial functions. You were introduced to those basic functions. What do we call this one? Linear function. What distinguishes a linear function? Say again? Okay. The main thing is the variable only has exponent of 1. Remember, quadratics, maximum exponent of 2, linear, maximum exponent of 1. Okay? What's the second one? Constant function. What distinguishes it? No variable at all. In other words, the maximum exponent for the variable is a 0. X to the 0 is 1. No x there at all. And then this one, what do we call that? The squaring function, which is the simplest form of a quadratic function, because its maximum exponent is 2. Those functions are examples of polynomial functions. The other polynomial functions can have larger exponents, more exponents, but they all have to be whole numbers. No negatives, no fractions, no decimals for the exponent. Coefficients, yeah, they can be fractions, decimals, positive, negative, it doesn't matter. Okay. But those are polynomial functions of the simplest kind. So here's the definition of a polynomial function. Let n be a non-negative integer. Okay, notice what I said? Non-negative, you can't have a negative exponent. Integer, you can't have a fractional or decimal exponent. They got to be whole numbers. Now, your coefficients are represented by the a's. Now, when you did see a subscript of a number or a parameter or something, usually that's just a marker. It's not really part of the problem except identifying where something goes. So a sub n means the coefficient for the variable, usually x, whose exponent is n. This just identifies this is the coefficient that goes with the exponent whose coefficient, whose power is n. A to the n minus 1, all the way down a2, a1, a0. Those are real numbers. That means they can be positive or negative, fractions or decimal, rational or irrational. Any real number. With one exception. That first one, a sub n, cannot equal 0. Any idea why that one can't be 0? It can be positive, negative, it can be fraction, decimal, it can be rational or irrational. It just can't be 0.
So out of all those, that's the only one that can't be 0?
Yes. All the rest of them can be anything. Here's why. Okay? What we're doing is identifying a polynomial function of x, that's the variable, with degree n. If that a sub n is 0, that polynomial is degree n minus 1. So to be degree n, that requires that that first coefficient can't be 0. Otherwise, it's not a degree n. is degree n minus 1, or something less, but not n. So that's the reason that can't be 0. So there's how we write our polynomial functions. These are real numbers, anything, positive, negative, fraction. These are integers, positive integers. All your exponents are positive integers. Polynomial functions are classified by degree. This one would be degree n, the maximum degree. That's the degree of your, that's how we classify. For instance, a constant function, what degree would that be? Say again? Yes, it's degree 0 because it doesn't have any variables in it. It's degree 0. Linear function? Degree 1. So a linear function, a function degree 1, a polynomial function degree 1, those are the same thing. In this section, we'll study predominantly second degree polynomial functions. We gave the definition of all, but these are called quadratic functions if the maximum degree is 2. Okay? Are these quadratic functions? F? Yeah, maximum degree 2. How about G? Yeah, now the X looks like it only has 1, but if you expand this, square this binomial, that will wind up with a maximum degree of 2. How about this one? H. But that has a coefficient of 1/4. That doesn't matter, you tell me, because coefficients could be anything, degree. So yes, it is a quadratic. How about K? The fact that the coefficient is negative, does that bother you? Not at all. Good. Okay. How about M? Say again? Yes, it is, because when you FOIL this, or multiply it out, you'll get x times x is x squared. That's the maximum x power degree of x you'll have, so this is a quadratic. Note that the squaring function is a simple quadratic function of degree 2. They don't show it, but we had that on the previous slide or two. Any questions? All right, so here's our definition of a quadratic function. Let a, b, and c be any real numbers as long as a cannot be 0. Why not? If a was 0, would that be a quadratic function? No, it would be a linear function if b wasn't 0. So for it to be a quadratic function, that first coefficient can't be 0. Okay? Now, we like to write them that way. We're used to writing them that way. However, I'm jumping ahead now, that's not going to be our standard form for a quadratic function. There's a reason for that. We'll get back to it later. The graph of quadratic function, I think we've already hit this before, is, I don't really like the term U-shape, but that's about the best way to describe it. I would more like to call it a smooth valley shape. Okay, the strange thing to call it. Because U, the tines on the U go straight up. Quadratics, they always are going outward. Okay? But what they're saying here, U meaning it's smooth at the bottom. It's not V-shaped, it's U-shaped. Okay? That's called a parabola. Okay? Parabolas occur in many real-life applications, especially those involving reflective properties of satellite dishes. Have you ever noticed the shape of a satellite dish? Okay? It's parabolic. The thing about a parabola, and parabolic mirrors in general, and that's basically what it is, any rays that come in parallel to a parabola, when they reflect off the surface, they go to one single point called the focus. And that's where they stick that little receiver at the focus of that parabolic receiver, and all the signals from the satellite get reflected back there, reinforcing, strengthening that. And that's why it is. Any other examples you know of parabolic reflectors? Any of you ever use a flashlight? Doesn't the beam sort of go out straight? Well, that's because the bulb is now in the focus, and the light going off the bulb reflects off the parabolic mirror behind the flashlight, and it goes out pretty much in a parallel beam. Same thing with your headlights on your car. Parabolic reflector. Okay? Lots of things. Okay? Flashlight reflectors. I didn't know they were saying that. Any of you ever shot a basketball? You know the path that basketball takes? Except for a dunk. Okay? So your dunks, they don't count on this, but you know, the rest of them. Yeah, right. Okay. All right. You know what path those basketballs take? Parabolas. Okay? Every time. Okay? Very close to one anyway. Okay? Golf ball, parabolic arc. Everything. Throw a baseball, hit a baseball, parabolic arc. Okay? Always, if it's in the air. Fly balls, we'll call it. Okay. Those are all parabolas, by the way. Now, all parabolas are symmetric. Now, we're talking about a different kind of symmetry here. Before we talked about symmetric about the y-axis or the x-axis. Now we're talking about symmetry around something else. Guess what? The axis of symmetry. Okay? Or simply the axis of the parabola. Now, because a parabola is that nice, regular, kind of U-ish shape, okay, then you notice that if you draw a line smack down the center of that thing, what's on the left looks just like what's on the right. Right? That means it's symmetric about the axis. Okay? Now, the point where that axis, smack down the center, intersects that parabola is called the vertex. In this parabola, what can you tell me about the vertex there? It's the minimum value. Lowest point it can go. Is this a parabola? It's not a U, it's a arch, but guess what? That is a parabola too. And it has an axis of symmetry. What's on the left is just like what's on the right. So guess what the vertex is there? The maximum point, the highest point on that. So your vertex, which is an important point, is also your either maximum or minimum point for that, the graph of that parabola. Now, what's the difference between these two graphs? Besides this is going up, that one's going down. What makes that true? If you look at their standard form, not standard form, their form, ax squared plus bx plus c, ax squared plus bx plus c. That looks the same. What's the difference? What's that? Okay, the a, that leading coefficient, a, in this case, is a positive a. In this case, it's a negative a.
Is there a maximum on, like, the one on the left side?
No. It's going to infinity. The further out you go away from this axis of symmetry, the higher and higher it goes, and it never stops.
I didn't know if the maximum would be infinity, but this just...
Well, infinity is not a number. That's a concept. It just keeps on trucking to infinity and beyond. No, y'all wouldn't remember that. Okay. All right. Okay. And there's no minimum for the second one. Okay. Good question. Okay. This is what happens if a is greater than 0. This is what happens if it's less than 0. What happens if a is equal to 0? Say again? Okay. It's not a parabola because it's not a quadratic. Remember, a can't be 0. That's a trick question. Okay. A cannot equal 0 for it to be a quadratic function or whatever. Okay. Now, when the leading coefficient is positive, we've already talked about this. What can you tell me about the graph of this? You can tell me several things. It's a parabola. If it's positive, it's opening upward. Okay, very good. So parabola that opens upward. When the leading coefficient is negative, is it still a parabola? Yes, it is, but now it's opening down. Got it. The simplest type of quadratic function is, it's not quite the simplest, but close to it. F of x is equal to ax squared. Really, the simplest is a is equal to 1. Then the next simplest is a equals something other than 1. Okay? And that a could be positive or it could be negative. What could you tell me about this parabola that differs from those two? Possibly, anyway. What point does that go through that you know it does? it goes to the origin, 0, 0. This, if B and C are anything other than 0, they won't go through the origin. Well, the origin won't be the vertex. Let me put it that way. That one, the origin's the vertex. Okay. Now, the one we just saw, the vertex is 0. When A is greater than 0, this is the one, alpha of x equal A x squared. That simple problem. A is greater than 0, this is how it looks. Now this one they've drawn here, just looking at these points, that A is equal to 1. So the first point is 1, 1, the next point is 2, looks like 4. So that's going to be a 1. But it could be any A. Okay? The second one there, the A is, all you can tell me now is negative, because it's opening downward. The maximum is now the origin, 0, 0. Okay? And it's opening downward. Now this one, yeah, it still looks like that to be -1, -1, and +1, -1. If A was negative 1, that would be what it would be. But it could be flatter or thin, skinnier or whatever. We've done that kind of stuff before. Okay. So when A is greater than 0, the origin is your minimum value. When A is negative, the origin is your maximum value. Okay. Any questions? All right. Now, when you sketch the graph of this parabola, it says it's helpful to use the graph of your simplest one, which is your squaring function, as a reference. Frankly, I think that the earlier ones, that one was the squaring function. What will an A greater than 1 do to that? This is from the last test, last chapter. That's a what? Stretching, a vertical stretch. What if the A is between 0 and 1? A vertical shrink. It gets flatter. Vertical stretch, it would get narrower. A vertical shrink, it would get narrower. It doesn't go up as fast. And of course, if A is negative, it flips over and goes downward. Then you have a downward parabola. And if A was a large negative number, it's a vertical stretch again. If it's a small negative number between 0 and -1, it's going to be a vertical shrink. Okay? So that's why they say it's usually helpful to plot the y is equal to x squared as a reference. Not completely necessary, but it does help. So let's do that on our first ones here. Okay. Which this package doesn't have graphing capability, so I'll have to just draw this out. Let me get my pen activated here. Well, there we go. Why did I put the x-axis way down there? Yes, because A in both cases were positive, okay? So let me just tick off a few points. 1, 2, 3, 4, 6, 7, 8, 9, 10, 12. Okay. Whoops, that's not very good at y-axis. 2, 3, 4, 5, 6, 7, 9. I don't need all those. Maybe. Okay. Now, it says, sketch the graph of each of these quadratic functions, comparing it with the graph of y is equal to x squared. What do you reckon the easiest one to do first? Y is equal to x squared. Give me a few points for it. 0, 0. 1 what? 1. Second? Okay, 2 what? Second? 2, 2. If you plug in a 2 for x, what? 2, 4. Okay, that would be somewhere about right there. Another one? 3, 9. There's 3, 4, 5, 6, 7, 8, 9. I think it's somewhere about there. Okay. Next. -1, what does that give you? 1. Okay. -2 would give you 4. Negative 3 would give you negative 9? Positive 9, okay. 5, 6, 7, 8, yeah, okay, somewhere about there. I may not be over far enough, something like that. And if we could get 4, it would be the 16, and that goes off scale. So basically, it looks something like that. Maybe a little better, but not too much. Now, I want to point something out to you. What's one of the first things you probably could have done with that? Find the A of S. What would that be? Axis of symmetry. What would be your axis of symmetry? So again?
The y-axis.
The y-axis is your axis of symmetry. Let me give you another way to say that. X equal x equals 0. Yeah. Because x equals 0 here, and here, and here, and here, here. All of that, x is 0 at every point on the y-axis, right? It's not going right or left. So, since you found the vertex to be 0, 0, whatever that first coordinate is of that vertex, x equal that is your axis of symmetry. In this case, it's 0, 0. So, once you had picked out 0, 1, 2, 4, 3, 9, you didn't really have to go back and plug in the rest of them. You've gone to the axis of symmetry, and this is 1 on the right, the 1 on the left. 2 on the right, 2 on the left. 3 on the right, 3 on the left. You just cross the axis of symmetry the same distance. That's what makes it a symmetric axis. So that's how the easy way to do it. You know, once you know what the line of symmetry is, and to get the line of symmetry, figure out what the vertex is. Okay. So let's do F. What color you want to do that one? Say again? Red. Bright red or dark, dull red? I thought so. Okay. All right. So we'll do F in red. Okay? Now, there is an easy way and a hard way to do this. Which way y'all want to do? I knew you would. Okay. Forget him. Okay. All right. The hard way would be plug in the values again, and it's perfectly legitimate. But the easy way is just noting that whatever your values here were, you're taking 1/3 off. So if this was 1, 1, it'll be 1, 1/3. Right? So let's do it the easy way. There's the first one. 1, 1/3. Negative 1, 1. Oh, I'm just going to use the axis of symmetry and go across there. What was 2? It was 4. And now we do, second, 4/3. And 4/3 is 1 1/3. So something about there. And across the axis of symmetry, right about there. Okay? And 3 was 9, and 1/3 of 9 is 3. So right about there, and go across the axis of symmetry, and right about there. Okay? Now if we had done 4, what would that have been? 16, and 1/3 of 16 is? Second? 5 1/3, exactly. So that's 1, 2, 3, 4, 5 1/3 would be something here over 5, over, get out of there, and over here. These things are so aggravating. Something like that. I may not be right on the money. And if we had done 5, 25, and 1/3 of 25 is? Second? Maybe 8 1/3. Okay? So that would be 1, 2, 3, 4, 5, 6, 7, 8 1/3. And that would be over 5. So it would be something like that. And by our symmetry, it would be over here, if that's 5 over. Okay? If we had done 6, what would that have been? 36. And 1/3 of that would be 12. That's 9, I think there. 10, 11. Ooh, just barely got that one in. That's over 6. I can't see it on that one, okay? And over here, over minus 6. So I'm just going to guess it. And there is your kind of f of x equal 1/3 x squared. How about g of x? What color you want that one? Blue. Light or dark? Huh? Light blue. Okay. Carolina blue. Never mind. We won't say that. Okay. G will be sky blue. Okay. Now, what are we doing here? Yes, your y value, for any x value, the y value gets multiplied by 2. 0 multiplied by 2 is 0, just like 0. 1/3 of 0 is 0. I forgot to put that one in. If you go 1 here, it gets multiplied by 2 and becomes 2. And across the axis of symmetry, it becomes 2, 2. Okay. If you like frilly things, 2, 2. Okay. This one was a 4. It gets doubled to be an 8. So it's there. Or across the axis of symmetry, there. Something. There it is. Okay. This is not liking to show up. Okay. Something like that. Okay. And then 3 was, but you double that, off scale, so 18. So this is one doing like this. And just like was said earlier, vertical stretch. Okay? So there you have it. 1/3, a vertical shrink, 2 vertical stretch. Theirs may not be quite as pretty as this one, but give them a break. They're limited. Okay. So let's erase this. Any questions before I move it? Okay, let's see how they. Oops, that's not what I want them to do. There we go. Here is, they did in light gray. The y is equal to x squared. Got it just like y'all did. And then compared with that, they did 1/3 of that. And it shrinks vertically everything by a factor of 1/3. 1/3 of 0 is still 0. 1/3 of 1 is 1/3. 1/3 of 1 is 1/3. 1/3 of 4 is 1 1/3. 1 1/3. So you see how it's vertical shrinks. Make sense? And then for 2, we're going to double the y values. Stretches by a factor of 2. Stretches the y. X's stay the same, 0, 0, stay 0, 0. Y side is 0, 0. Okay, 1, 1 now becomes 1, 2. Negative 1, 1 becomes negative 1, 2. 2, 4 will become 2, 8, somewhere way up there. So that's a vertical stretch for G of X. Any questions? Make sense? None. Okay. I probably ought to have my book open to the right page so I can make sure I'm not skipping anything. All right. Now, that's example 1. In example 1, note that the coefficient A determines how wide the parabola f of x is. If A was a small number, it gets wider. A larger number gets narrower because of stretching and shrinking vertically. Now, when this absolute value of A is small, and what we mean by that, less than 1, the parabola opens wider than when the absolute value of A is large. Usually by that we mean greater than 1. Okay? Now, we know, what does this one do? Y is equal to f of x plus or minus c. What does that do? A what? That's not a stretch. It's not multiplied, it's added or subtracted. That's a what? It's not a stretch. A stretch is multiplied or divided. A shrink is divided. Shift. Okay, I'm sorry, I can't hear well. Okay, which way would the plus be shifting? Aha! Okay, remember, y it would go the way you think with x is not. So a plus would shift to the left c, a minus would shift to the right c. That's if c is positive. We'll assume that. What does this one do? This was adding or subtracting from the x, which is the horizontal variable. This is adding or subtracting to the y, the f of x, which is y. So this would be a vertical shift, yes. What would the plus do? Go up. Y is going in the right direction, and the minus would go down. What would this do? Reflect across the y-axis, okay? Because you're negating your x, so it goes across the y-axis. This one would be negating across the x-axis because you had a positive, it became negative, or you had a negative, it became positive in the y. So it reflects across the. Those are rigid transformations. Why? What is true about rigid transformations? The basic shape doesn't change, it just moves around, okay? Or flips over, or, that kind of stuff. But the non-rigid transformation, those are the ones that expand. Those are the things that squeeze or stretch or shrink or that kind of stuff. So those are the rigid. And that lets you know, in the simple form, we know that always goes to the origin. But add something to it, usually it's going up or down. Add something to the x, and it's going right or left, and you can have all those things going on. Okay? So, that's how we get parabolae that are not on the origin, or the vertex on the origin. For instance, these figures below show how the graph of y is equal to f of x, that's our standard parent function here, for the squaring function, x squared, y is equal to x squared, can be transformed to produce f of x, which is y is equal to minus x squared plus 1. What's happening there? The minus reflects across the x-axis, and then the plus 1 shifts up. And that's probably the best way to think about it. Otherwise, if you shift first, then you don't reflect across the x-axis, you reflect across the vertex. So if you shifted this up first, then you have to reflect across the vertex, not across the x-axis. So probably best to stay closest to the x. Do the reflection first, then add the 1. Okay? So that would be minus that. Now, this one here, what's it doing? Left, how much? 2, and down 3. So shift left 2, down 3. There's your new vertex. Here's your new vertex there. This one didn't have a reflection because the x stayed positive. X squared term stayed positive. Does that make sense? All right. Saw that on the last test, didn't you? Okay. You'll probably see them again, won't you? All right, now we move on to the standard form for a quadratic function. Now, we've been talking about quadratic functions as if they were ax squared plus bx plus c. And sure enough, they are. That is a quadratic function. But I want to invite you to think back, because I know you've done linear functions sometime in your past. And what the books used to call, they actually called it the standard form, which I don't like, but they did. Let me go back to black here. Of a linear function, they would sometimes say ax plus by equals c. Is that a linear function? It's not really a function, a linear equation. Yeah, both of the variables with maximum exponent of 1. That's a linear equation. And you can plot that. Do those a, b, and c tell you anything really crucial? No, it's pretty much a worthless form. And yet the books called that the standard form. What form for a linear equation told you a lot more information? Ha ha, very good. You could change this to be y is equal to mx plus b. That's not the same as that b, it's a little b. What did that tell you? It told you the slope, and the y-intercept. It told you everything you needed to graph the function. The first form told you almost nothing you needed to graph the function. So when we went back to what we used to call the form for a quadratic, f of x is equal to ax squared plus bx plus c, guess what? The a tells you a little something. What does it tell you? Which way it opens, whether it's plus or minus, and skinny or flat, okay? So it tells you about that. That's all it tells you. B and C, what do they tell you? Next to nothing. So that's not a very useful form. It's the one we use a lot, but it's not very useful. Now, if that was an equation, you set it equals 0, yeah, that helps you factor. You use the quadratic formula. Yeah, we love that form for an equation. But for a function, it's not that useful. So here's what we do. We write the standard form for a quadratic function to be this. Now, guess what? That A is the same as that one, so it's going to tell you exactly the same two pieces of information. What are they? Which way it opens, whether it's plus or minus, and whether it's skinny or fat. Okay, I don't like to use those terms. Okay, now, we've replaced the B and C by two other parameters called H and K. Now, what you reckon they could be? Anyone want to make a guess? What we're saying this did? What does that represent? A horizontal shift. Of what? The whole parabola, but particularly, what's the most important? The key point to get the vertex. This H tells you where that vertex is shifted, because it was a 0 there, right? In the simplest form. Now that tells you how far it's gone. B told you nothing, okay? And what did this tell you? The vertical shift. It told you where the vertex went, up or down. So now this H and K, that is your vertex for the parabola. And guess what? If you know the vertex of the parabola, really important to start. Then if you know A is positive or negative, you know from the vertex it's going up or from the vertex it's going down. And if A is a large number, with a positive or negative, it's going to be going up real quickly or down real quickly, or if it's a very small number, it's going up slowly or down slowly. So yeah, this form tells you a lot more about how to graph than that. Just like this form told you, same equation, but these parameters, these variables, these parameters, M and B, tell you how to graph it. These tell you how to graph it. A, B, and C, except for the A, doesn't tell you much. This form is especially convenient for sketching the graph of parabola because it identifies the vertex of the parabola, HK. Now, again, H is associated with the X variable, and K is associated with the Y variable. And guess what? It's the opposite of the H, that's the vertex, and what K is, that's the Y variable. So again, whatever the X coordinate is, do the opposite of it. So if it's X minus H, it'll be H. Plus K, that'll be K, okay, HK. So the standard form for a quadratic function, not for a quadratic equation, it's a quadratic function, is A times X minus H squared plus K, as long as A is not equal to 0. Because if it's equal to 0, it's not a quadratic function, okay? It's a linear function. Okay, and this is called the standard form. The graph is a parabola whose axis is, tell me what the axis will be. X equal H, exactly, okay? Because that's the X component of your vertex. In fact, take this little thing here and just put an equal sign, and you've got the vertex, the X coordinate of the vertex. And what's the Y coordinate of the vertex? HK is your vertex. Now, when A is positive, opens upward. When A is negative, opens downward. You know that. Okay. Any questions? To graph a parabola, then, it's helpful to begin with writing the quadratic function in the standard form. Not the good old form, but the standard form. Now, how do we do that? You remember back, some of you may not have taken Math 100, but if you did, good on completing the square. The rest of you, if you didn't take it, you probably had it in high school. That was our favorite way to solve quadratic functions, wasn't it? Completing the square. It was usually a little more involved, and once we got the quadratic formula, you thought, I'll never do completing the square again. Wrong. Okay, you're doing it now. So we're going to do it in example 2. In this example, notice that when completing the square, you add and subtract the square of half the coefficient of x within the parentheses instead of adding the value to each side of the equation. When we're solving equations by completing the square, usually we did sides of equations. Now we're going to do it all on one side. So let's proceed. Says sketch the graph of that. Okay? Now, Tyler likes to work hard. So he's going to pick x's and plot y's and do it that way. Right? Of course, yeah. Okay. Let's be a little bit lazier. How might we do? Do a little work up front. It'll save you a lot in the end. What you reckon you got to do first? Maybe remember what the standard form looks like. What does it look like? F of x is equal to a times x minus h squared plus k. You got it. So what do you reckon the first thing we're going to have to do here? Let's factor out that a. That's the first thing you see there. The a is outside, away from the x. So that's what we're going to do first. So here's what I'm going to do actually before that. I'm going to rewrite this ever so slightly. F of x is equal to 2x squared plus 8x blank plus 7. Now, it has to be a really obnoxious blank, okay, for it to work right. Okay? I'll show you. And then, what do you think the next thing is? I just said it earlier. Factor out the 2. And that gives you x squared plus 4x blank plus 7. Right? That's why I did it. Because we want to complete the square. Do you remember how you do that? It was on that last slide. What's that? You factored out the 2 from the 2. See, separate the x terms from the constant terms. That's why I did the blank. Get the constant terms over there. Okay? Then factor out your a. Okay? From both terms. Now this gives you something we want to make that a perfect square trinomial. You remember what it takes to be a perfect square trinomial? Okay? Half of the coefficient for the x and square it. That's what we do. Okay? So in other words, where's your coefficient for x? 4. Take half of it. And that's a plus 2, by the way. Right? And then you square that and you get a 4. Okay. Now, I'm going to cheat a little more now. That 2 is on the outside. As soon as I take half of that 4, I write down here x plus 2. Okay? That's going to be my perfect square. Okay? Believe me. I sound like, no, I don't want to go there. Okay, we squared that and got a 4. Okay? Now, what did we just do? When we just had a blank there, that's the same as this, wasn't it? And that's the same as that, right? But what happened when we put a 4 in? We changed everything. What did we just add? Say again? No, yeah, but what did we add that changed this equation? It looks like a 4, but we have a 2 in front. We actually added 8. So to keep this the same function, we have to subtract 8 from the same side. Okay? Now, if you went back and did the work here, you'll find out that goes right back to being what we had is the same function. Okay? That's the key. That's what they were talking about here. You add or subtract the same and subtract the square of the half of the coefficient, blah, blah, blah. Okay. That's what they were talking about. Okay? So this becomes 2. This becomes x plus 2 squared. That's called completing the square. And this becomes plus 7 minus 8. Second? Negative 1. Perfect. Guess what you've got? You got your standard form. What does it tell you? 2 things. What does it tell you? What do we got? The parabola is facing upward because the 2 is positive. That's something. So A is equal to 2. So parabola is going up. But you see, that's A equal to was still here. Yeah, it's still up. Yeah, that's good. Okay, you got both a horizontal and a vertical shift. What point can you identify here? The vertex. And that's what the V is there for. Hint, hint. Okay. What is that vertex? Say again? Almost. Remember anything dealing with X? Negative 2, negative 1. Remember anything dealing with the X? It's the opposite, okay? So it's negative 2, negative 1. We got the vertex. We have the A. We're ready to roll, aren't we? Okay? So sketch the graph. Where should I put the x-axis? Huh? Down low, but not too low because I have to get this on it. So let me put it down here. Because I have to go down at least minus 1 to get to my vertex. And over here, minus 2 to get to my vertex. There's my vertex. Most important thing to graph. Okay? And tick off my other points here. That means hack them off, you know, I made them mad. Okay. And I don't need that one, but... Okay. I found my vertex. Now, in my mind, there's one other thing that's really important to plot on here right now. Any of you want to make a guess of what that is? The A of S? The what? What you call it? The axis, okay? What color you want the axis? I don't want it confusing the thing. Pick a color. Green. Light or dark? Dark, okay. So where do I put that axis of symmetry? Vertically through the vertex. And I'm going to write it down too. The axis is, how would I write that? I wrote it that right there for a reason. Say again? X equal negative 2. That's your axis of symmetry. I don't need it in a parentheses. Why did I do that? I don't know. Okay. X equal negative 2. That is your axis of symmetry. Because it's whatever the X is. So I'm going to do this. Everywhere X is negative 2 is on that green dotted line. The only point on the parabola is the vertex. But we're going to use that in a minute. So let's go back to black. All right. Now, there's a couple ways you can go from here. Okay? I'll show you one way. Yeah, we'll just stick with this one way. Okay. In this standard form for the quadratic function, we started at the vertex. And we identified that to be negative 2, negative 1. Okay? Now, where I like to go next is go either one to the right or one to the left of that vertex. what's going to be true about which way you want to go, right or left? I don't care. Second? Right, okay. What's true about going one to the right? What can you tell me? Yeah. What is x equal to? -1. Perfect. So let's plug in a -1 here. Okay. I like this form better. Tyler likes that form up there because it's harder. Okay, but I like this one better. I'm lazy. Okay, he's not. He's a hard one. Okay. So you put a -1 in here, and what do you get? -1 plus 2 is 1 squared is 1 times 2 is minus 1 is 1. So guess what? We got our next point. X equals -1, the y is 1. Now what does the axis of symmetry do for us? Just go on the opposite side of that, but stay flat, stay level, and put 1 there too. That's why I said you could go right or left. Doesn't matter. All right. Now I want to go 2 to the right or left, but I have a preference on this one. Where would you like to go, right or left? Second? Okay, she wants to go left. She's another hard worker. Okay, it's really positive. What happens if you go right 2 from the vertex? Where are you then? The y-axis. What's true about the y-axis? X is equal to 0. Very good. Now, in this case, I don't like this form. I'm going to join Tyler here, and I'm going back to this form. What happens if I put an x equals 0 in here? What? What's equal 7? Y. F of x is y, isn't it? Y is equal to 7. Hey, we got it right there. What do we call that point? Y-intercept. You say x equals 0, and that form is always easy to do. I would do that maybe right off the top. 1, 2, 3, 4, 5. I can't even figure these out. 1, 2, 3, 4, 5, 6, 7. Right there. That point. Okay? And what else can I do? And if we had followed Brianna, we would have been there, but yeah, go 2 to the left, and there you have it, which was easier. No, never mind. I won't rub it in too much. Okay. All right. And then, guess what I would do next? Go 3, right or left to the vertex. Which way you want to go? It really doesn't matter. To the right. I'm convinced. What are we then? Where are we then? X equals 1. So I'd like to go back here. So it wouldn't be bad up there either. In fact, that's pretty easy up there too. But let's do it both places. X equals 1 here, what do you have? 3 squared is? 9. Times 2 is? 18. Minus 1 is? 17. Okay, let's see what would happen if we put a 1 in here. That's a 1, that's a 1. What do you have? 17. Yeah, it worked both ways. And that's off scale, so I can't plot it anyway. Okay, but you get the general idea. Here is your parabola. Coming down here, and then going back up here, and up. There it is. See how the vertex is the best place to start. Axis of symmetry, get that in there. Then pick some points. And be pretty judicious about your points. Just 1 right or left of the vertex, and go from there. If you can find that y-intercept, use it. Okay, that's easy to do. Okay, and then go from there. And use that axis of symmetry to just plop across the x-axis. I mean the axis of symmetry. Okay. I know it sounds like people are beginning to close the wagons here. Let me erase this. Let's just see how they did it. Okay, they wrote it down. Okay, good for them. Then they factored out the 2. They didn't leave the blank. Shame on them. Okay. Then they took half of the 4 and squared it, and then they added and subtracted inside parentheses. I think that's sort of dumb. Add inside, subtract on the outside. Okay, and that's what they wound up doing. And sure enough, they pull the minus on the outside, and they get the same thing we did. They use the vertex, -2, -1, and then they plotted it. They didn't have as much fun plotting as we did, though. Okay. All right, homework exercises. Oh, let me not forget those. Let's do any of the odds 7 through 11. Actually, I would do all the numbers 7 through 12. The 7 through 11 odds are in the back. And then 13 or 15. And 17 through 33. And stop there at 33. Good deal. Okay. Let me, if I could get someone to punch that button twice, the bottom button there. No, the bottom. That. Hit it twice. 1, 2.
Is it okay if I
Again. Oh, you got it. Okay, second. At 4? Okay, I'll probably still be here. Okay. Oh, yeah. No, wait. I'll be in class at 4.
Well, what time can I come before you?
Okay. Well, why don't you come at 4, and it won't be a big interruption. I'll find another classroom for you to go to. I'll be here teaching at 4 o'clock. Yeah.
Okay.
So I'll just try to remember to bring yours up here with me. If not, I'll go down to my office and get it. I'm sure the students will be glad to have a little break. Okay. All right. Okay. Y'all are ready to go. Let me get this stopped.